commonly what you've got is the button part, the front piece, and then you've got the switch part on the back piece. Okay? And the reason you have that is so that you can add whatever type of switch you need. You can have multiple switches with one push button. Okay? So I'll pass this around as well and see who hasn't got it first. Pass this around. It's an Allen Bradley switch. Oh, thank you. And it looks a lot like what's on the screen. Okay, so here's a simple way of wiring this system without a PLC, but it looks like ladder logic. Okay? Basically, there's 120 volts AC across these two legs. If you touch those two together, you short it out. You don't want to do that. Okay? And so the way it's set up is the pressure switch is wired in line with the temperature switch, and then in line with the motor and an overload cutout, so that if too much current goes through the motor, the overload would open up and the motor would shut off. Typically, the overload is built into the motor itself. Usually it's a thermal overload. So what kills motors is heat. And so if the motor overheats, you want it to shut down so it doesn't fail. Now there's a manual push button. This thing is wired in an OR, or a branch configuration. You see how that works? If the pressure switch is on and the temperature switch is on, then the motor will turn on. Or, if the push button is pressed, then the motor will come on, of course, assuming overload hasn't picked it up. Okay? Now, I use those words very specifically because we're going to use logical terms of and, or, and not. Okay? We're going to use those very specifically a little bit later, starting to include that vocabulary. Okay? You understand how this circuit works? Pretty easy, pretty straightforward. And the reason that ladder logic was created is so that you can make something that looks like that in the PLC. So what we're going to do instead, we're going to use a PLC, and we're going to wire the pressure sensor up to an input. We're going to wire the temperature sensor up to another input. These are just on-off things. We're going to wire the manual push button up to a third input and apply voltage across them so we can activate the inputs to the PLC. Okay? All that would be wired to an input module, kind of like one of these. Now, you guys are probably falling asleep, so let's take a real quick short break. Stand up, come up here and look at these PLCs so you can see what I'm talking about with input and output modules. I want everybody to come up and have a look. I wish they were separated out so you can all see, but okay, so this is a 120 volt AC input module, and this is a 120 volt, 220 volt AC output module. Okay, so if we're wiring up inputs, we wire them up to this one, or this one, or this one, all three of these ways. So that picture over there is that field devices are hardwired to an input module. That's what they're talking about, is this kind of input module. Make sense? Okay. On the other hand, where we're going to hardwire things like the motor output, we would wire that to an output module. Okay, so that's something that's separate. Does that make sense? Okay, thank you. I woke you up, I hope. I make you get up. By the way, I'd like for this class to be more of a two-way conversation. So if you want to ask a question or say anything, please raise your hand. Don't let me just talk to you, because that'll be boring. Also, if you don't understand something or you've got any problem, please ask. And if you're falling asleep, feel free to stand up. That's not a problem. I personally have a lot of trouble. If I'm sitting down, I'll tend to fall asleep. If I were a truck driver, I'd be dead by now. Yes?
I remembered what that one smackdown was, the limit switch. I totally forgot what the whole.
Oh, okay. Okay, makes sense. Thank you. So with that little extra triangle on it, then it's a limit switch. Thank you, makes sense. Okay, so instead of hooking up the switches and the motors and everything directly, instead we wire them as inputs and outputs to the PLC, and then we make the same kind of ladder logic inside of the PLC that looked just like it did before, where this input 1 is connected to the pressure switch. Okay? Input 2 is connected to the temperature switch. Really what these are instructions that reference the memory address that those switches are connected to. That's what they really are. The manual push button is on input 3. Okay? You can see when you press the input on the push button, input 3 would go true. That would make contact here, which would turn on this output, which output is connected to the motor. So it does the same thing that the last circuit does. So why on earth would we spend the money for the PLC as well as all these industrial controls and inputs and outputs? The reason we would spend the money on it is because it's very easy to change the program. Okay? And here's a simulation of the thing in Logix Pro. I don't really want to go through that. Okay, so let's say that we don't like the way it works. Let's say that we want it to work differently. So that the temperature switch has to be true before the motor can be activated. See how this is different? If the pressure switch is true, or if the manual push button is being pressed, if it's true, and if the temperature switch is true, then the motor can come on. We cannot bypass the temperature switch anymore with the push button. Okay, that may be something that's important for safety. Okay, so we may have wired it up originally and realized, oh, we've made a mistake. We've got to rewire it. Well, it's a whole lot easier to change the PLC program. Plus, the PLC gives us a lot of flexibility and capability that the wiring does not. Let me make sure I didn't miss anything. Yeah, there's nothing else here. Okay? All right, so then the author of these slides went through and showed how to implement that in ladder logic. All right, so really a PLC and a computer share the same type of architecture. They both have memory, they both have CPUs, they both require power, but the key difference is that a PLC is typically not as affected in an industrial noise or an industrial environment by noise, whether it's electrical noise or mechanical vibration or humidity or any of those things that really affect a normal computer. They don't affect the PLC near to the same extent. Okay, so they're very hardy systems. Also, quite frankly, in my opinion, ladder logic is a lot easier to learn than the typical programming languages for a normal computer. And once you get the hang of it, and you start thinking in a logical fashion, it's not too difficult. Now, unfortunately, they typically do not have a keyboard or a monitor or anything like that permanently connected. Computers, on the other hand, are much more complicated and capable of doing multiple things simultaneously, whereas a PLC typically executes one program over and over. Okay? Now, I don't remember if that's in the slides or not, but it is true that computers are beginning to be used in place of PLCs. Okay? That's something that's happening. The reason it's happening is because computers, quite frankly, are dirt cheap. You get a whole lot more functionality with them. If you go to process where it's not critical, you don't have to have the high reliability that a PLC offers. The computer may be an acceptable solution. A former student of ours has been very kind and has come back and has seen us a couple of times and visited with us. He works for Boeing, or he did. I think he works for another company now, but he loved airplanes. He was determined to work for Boeing, worked hard, got internships, and moved out to Seattle once he was graduated and worked for Boeing. Great kid. Man, sorry, I'm old. All you guys are kids here. But anyway, he moved out, worked for them, came back and visited us, and was talking about some of the systems that were on the particular aircraft he was working on. He was working on a military aircraft, which was part of the Boeing support team. And he was talking about how they recorded data on this aircraft. Well, it turns out they were using reel-to-reel tape. Okay, this is today. This is not 20 years ago. They were using large reel-to-reel tape. And they were actually using a computer as well, but the computer they were using was running Windows 3.1. Anybody remember Windows 3.1? Okay, it was probably before most of your time. Okay, the reason they used Windows 3.1 is because they had worked out all of the bugs. They had put this particular combination of operating system software and their own software through so many phases, through so many reliability tests, and worked out so many bugs. They would not allow any updates to that machine. That was out of the question. There's no way, because it was reliable, and you had to have a reliable system for this aircraft to function properly. Okay? So, anyway, some situations need very high reliability, and quite frankly, computers just aren't there most of the time. I'll skip over this. PLC systems are kind of nice. You may have noticed, it may not have a monitor, but on the front face of this are actually LEDs. That's what these numbers are for. And when an input goes active, a light will come on to let you know that input is active. When an output goes on, one of the lights come on to let you know that output's on. Okay, so it's nice for troubleshooting. And also, typically, PLCs are set up to be easily replaceable. Now this one's not terribly easy to replace, but if you had a problem with an input card on this PLC, you can actually remove all the terminal blocks. They literally just unplug, throw in a new card, plug your terminal blocks back in. You didn't have to disconnect even one wire. And that's actually really nice, because if something goes wrong with an input card, typically the PLC is not the biggest part of expense of the line. Downtime on the line is what's expensive. So getting the PLC back up and running is critical. Okay. Let's see, is there anything on this slide I need to talk about? No, we've already mentioned all of that. Human-machine interfaces are becoming more common. Well, I mean, technically everything's a human-machine interface where you have start and stop buttons. My daughter's kind of lucky. She got 3 trips to Holiday World this summer through various means, and she's only 6 years old. And of course, I was there as an engineer, and I was looking at everything, and I enjoy riding the rides because I don't get sick on them. But also, I was looking, hey, look at that motor, that's awesome. You know, and look at those controls, this is cool. You know, so I was geeking out over all the controls. But anyway, all of the rides had an operator control panel. They had their own locks for lockout. They're not really lockout, they were more e-stop buttons with locks on them. But they had those, they had start-stop buttons, they had various indicators of what was going on with the ride. And they were fairly straightforward panels, they were fairly simple. But once you get into industry, you'll find that those kinds of panels are common. And sometimes they become more and more complicated, where you can go to the extent of having a whole LCD screen with a simulation of the process. And if there's a problem anywhere, something lights up and flashes at you so you know what's going on. So even touch screens are becoming more common as control centers. Okay? Some people still demand push buttons, but honestly, the human-machine interfaces are becoming more and more capable, more and more complicated. Okay? Let's see. Programmable automation controllers. This is really a pack, is what I was talking about earlier when I talked about the, what are they called? I had the word a minute ago. The Run Lab View. I mentioned it a second ago. It's not a PLC, but it's like a PLC. It has a lot more functionality. Basically, it's just a more functional PLC that's a little more ruggedized, but is more like a computer with more capability. All right, PLCs come in all shapes and sizes. You notice this one. This is not the smallest PLC on the market. There are smaller ones. This is not the biggest PLC on the market. There are larger. Okay, so they come in all kinds of shapes and sizes with many different options for inputs and outputs. Of course, cost is a big variable as well. But the input-output count is probably one of the most important features of the PLC. If you buy a PLC that's too small, it doesn't have enough inputs and outputs, it's not going to work in the machine that you want it to work with. Okay? So typically what you'll find is if you start designing a machine, you think, oh, I need 5 inputs and 3 outputs. In that case, just go ahead and order a PLC with about 20 inputs and 10 outputs, because you'll probably end up using it. Okay? What else? There are several different ways a PLC can be set up to operate. Basically, a PLC can be set up where you have one PLC dedicated to one machine. It only does one thing. Okay? You can have a PLC set up where it multitasks, or essentially it controls multiple machines. Okay? That's also possible. Another way of setting it up is so that the PLC is kind of like a master that controls other PLCs or other computers that themselves control machines. Okay? So there's several different ways of setting up a PLC to control a system. We're not terribly interested in that. I just wanted you to be aware of it. When I first started teaching this course, I probably made it a little too difficult because I made the students' main project to program a PLC that basically did this. Its job was to control other units that were operated. There were 5 robots in the system that had to be told to go, and you got feedback from those. Probably a little much, so just be glad you weren't part of that class. But anyway, that actually is something that can be done. The system I was modeling it after was a system I saw when I worked for Grody. I worked for Grody Industries in Madison, Indiana for about a year after I was at Amatro doing research engineering. But the system I saw was a system that was, it had been set up to automatically build one of their products. Okay? There was one human operator, and there literally were, let's see, 1, 2, 3, 4, technically 5 robots that operated in that system. And so the students had to program a master PLC to control the whole thing. It was an interesting project. I ran it for a couple semesters and then realized it probably wasn't appropriate for the class, because that's probably a little bit beyond what we're trying to do. Memory is an important thing when you buy a PLC. You need to make sure you have enough of it. The longer your program is, the more memory you'll need. Okay? There's one guy I know, I've known him and his wife since I was in high school or so. And his job, he made a pretty good living because his job was to control one PLC. He was the expert on that PLC, and if he printed out the ladder logic code for that, it was about that thick. Okay? So he had a couple, probably 10, 20,000 lines of code. He was the one that knew what every line of code did. If a change needed to be made, he was the one to do it. Okay? And that's how he made his living. By the way, I don't feel terribly bad about making you pay for the book, even though it's expensive, and buying the Logic Pro CD, because in the MET program, when you first come in, we teach you about CAD, so you can go out and get a job, making decent money, right, as an intern. If you learn this stuff, PLCs, you can make serious money, okay? PLC programmers can make really good money. So after you get through this class, the knowledge you have, if you go and become a PLC programmer, will pay for this book and the CD anytime. Okay? Anyway, when you select a PLC, it's important to have an idea of how long your program is going to be, so that you can make sure you get enough memory to operate the program. So it depends on how many I/O you'll have, the size of the program, how much data you need to store, what you need to do in the future, future expansion. Now in this picture, this is kind of old because it includes a backup battery. The job of this backup battery is to store what's in memory. Now today, you probably got a thumb drive on your keychain that can hold more than this, right? It's non-volatile memory. So that's becoming more and more common in PLCs. Modern PLCs really don't need a backup battery for the most part. And the only reason you need a battery is for keeping time, you know what time of day it is. Okay. Now, the instruction set, I think this is where I need to jump out of the slides, because this is going into talking about, this is going into talking about the various instructions that are used to program a system. Let me just go ahead and start doing some programming so that you can see how this works. Now, typically what I will do, let's see, I guess I'm going to reinstall it with this CD. It'll work. Uninstalled it. Normally what I will do before I give you an assignment, I will show you how to accomplish the assignment. I expect you to watch and try to understand. A lot of students will have Logic Pro running and they'll just copy what I do. If you want to do that, that's fine. I don't recommend it because I'll be glad to post my program for you. If all you do in the homework is you copy my solution, you're shooting yourself in the foot. Okay? Because on the exam, you will have to program. Okay? So the homework is your opportunity to learn how to do this stuff. Okay? So I want you to work through the homework yourself as well, but I will help you quite a bit by initially. Let's try it again. I should have tried that. I don't know why I didn't. Hey, go on. It doesn't like you.
This is why Windows doesn't run machines.
Exactly. That is exactly.
I use Linux.
I like Linux. I've got a Linux box set up at home that I use as my file server, and it is a lot more reliable than Windows. But I cheated. I went for Ubuntu because it was easy. Let's see if this will work. Anyway, typically what I will do is I'll start programming to kind of show you some of the vocabulary and help you understand and get started. Well, it was already running. I forgot about that. All right, let's go to the I/O simulator. Let's just start there. Oh, by the way, that little wizard that appears is very annoying. You can make him hide. If you leave your program open at home for a little while, he will go to sleep and he will snore, and it will come through your speakers and you go, what is that sound? Because it really doesn't sound like snoring. And then you finally discover it's coming from your computer and you think your hard drive is good. Anyway. I think that Microsoft got rid of Clippy, if you remember Clippy from the Microsoft.
Oh, yeah.
company. So it makes it look like it's kind of a joke, right? Well, this does the same thing. All right, this is the IO simulator. This is a very boring part of the program, but I'm going to start here so that I can show you a few instructions. Okay, the examine if open and examine if closed instructions, I can't remember which one's which, it doesn't matter. I'm going to show you how they work. Okay, I can hover over it, we can see. Examine if closed. Basically what you do is you put in an instruction as an input and another one as an output. Now how you arrange it depends on what you want. Let me just show you how this works. I want to make this switch turn on this light. Okay? So what I'm going to do is drag the address from here. By the way, in these simulators you can cheat. You can drag and drop. I'll teach you how to address all this a little bit later, but for now you can just drag and drop. Okay? I'll go ahead and tell you what it means. I stands for input, :1 /0. Well, :1 is this whole bank of inputs. Notice there are 16 inputs. Okay? Those 16 inputs map to what's called a word. How many people have heard of a word? Not a word like you would write, but a word in computer memory. What is a word? Well, computer memory is actually kind of comical. Okay? There's bits, which are binary digits that are either on or off. Okay? If you have 4 bits together, it's called a nibble. Okay? If you have 8 bits together, it's called a byte. I think people that develop computers are probably hungry. Okay? If you have 16 bits together, it's called a word. 32 bits and above is a long word, depending on what architecture. Okay? Anyway, so it's common to see 16 inputs because that corresponds to a whole word of bits, 16 bits. Okay? Anyway, the address for this particular input, this is one particular bit in memory. This is bit number 0. So input module :1, so it's word 1 has all 16 bits. Bit number 0. So /0 indicates the 0th input. Okay. Now you can comment your code, and I highly recommend you comment code. That's one thing that's common from other programming languages. If you don't comment your code, you won't know what it does in about a week. Okay, you will forget. Okay, unless you have photographic memory. So you can right-click and edit symbol and add in a note. Okay, like switch to turn on light. Okay, it's kind of a long comment, but there it is. Now this is made to look like a coil on a relay, whereas this set of contacts is made to look like a switch on a relay. Okay? But anyway, this is essentially inputs, and we'll essentially put outputs in those. Okay? So on that coil is what I'll call it. I want to connect this coil to this light. So I will do that by simply dragging the address over here. You'll notice the addressing works about the same way. I wish I could zoom in on this. I apologize. If you can't see, you might want to consider sitting up closer. Okay. But anyway, the way this address works, we're looking at an output module. So O, not 0, but O. Which output module? Well, :2. Well, that's this one. Okay. /0. That's this particular bit, this particular line. Okay. How many people have dealt with bits before? And ECETs all raise their hand. Well, a bit just means binary digit. It's something that's either on or off. We'll learn more about that next time. Let me put a note here. Light that's controlled by switch. I ran out of space. Now, since I'm simulating 2 things, I've got a laptop here, if you will, that's where I'm creating ladder logic, and I've got a PLC that's going to run that ladder logic. I have to download this program before it'll do anything. Okay? So what I'm going to do, I hit the arrow up here to get out of the command palette. I'm going to hit download to actually put that program, my ladder logic program, into the PLC, and now I will hit run. I hit run, and it's kind of anticlimactic. Nothing happened. Why? Well, actually what's happening is the PLC is scanning this over and over and over again. It's scanning it multiple times per second. It's reading this particular output and deciding not to, reading this particular input and deciding not to set that output because the input's on. Make sense? So watch what happens when that input goes on. Yay. We're going to switch the controls of light. Well, we've got a bunch of them on the walls. Right? So what? Well, we can make it more interesting than that. Let me change the program just a little bit. Did you notice there was a set of contacts that says examine if closed and examine if open? It's got a line through it. What's the difference between those two? Let's find out. I'm going to right-click this instruction and change it over to an examine if open. Now watch what happens. I'm going to download it because I've updated the program and hit run. Now the light's on. What's going on? Well, what the PLC is doing is it's looking at this memory address, which is word 1, bit 0 of the inputs file. Okay? It looks at that, it sees that there's a 0 coming in, and off. Okay? That slash means inverted. Okay? So it changes that to a 1, and it passes power to the output. Okay? So what do you think is going to happen when I turn the switch on? Well, if the switch is on, that's a 1. 1 inverted is 0. Set the lamp, it's going to turn the lamp off. It works. Nice. So basically, it's just inverting the state of the switch to turn the lights on. Okay, well that's interesting. Well, have you ever thought about how a doorbell works? You probably have a doorbell in front of your house and on the back door, right? Okay. So when do you want the doorbell to ring? When switch A is pressed or when switch B is pressed, right? Could we simulate that here? Sure. I'm going to program that with a branch. This is called an OR configuration. You can drag and drop these things quite nicely if you want. I'll need another switch to represent the back door. Call this front door bell switch and back door bell switch. Let's call this doorbell. Download it. It's really easy to see what's going to happen, right? Because this is a graphical programming language. Okay? And let me change the switches. You can right-click on the switches and ladder logics to change it from a switch on and off to a momentary on and off type of switch. So if I press the front doorbell, the light comes on indicating that the doorbell would be ringing if I wired it up to an actual bell instead. I press the rear door, and that switch comes on. Now what I like, let me change this so I can talk about it. What I like about ladder logics and RS logics is that when you run the code, you can see what's active and what's not. It will highlight whatever is active. Okay? So since this switch is on and passing power, then all the instructions, anywhere that memory location is referenced in my code, will light up. They'll come on and indicate that they're passing power. And any outputs that are active will also be highlighted. That makes it very easy to troubleshoot. Okay? Or at least it helps troubleshooting. Troubleshooting is not all that easy, or debugging is not all that easy. Now there are other types of switches. Let me just go ahead and show them to you. Here's a switch that is by default passing power. When you press this button, it stops pressing power, or it stops passing power. Can you imagine having a doorbell like that? You have to come to the door and push the button for it to stop ringing? That wouldn't be very good. Okay, but that's what we've got set up. Let me show you something else. Let me tease your brain just a little bit. I'm going to show you a circuit that is a very industrial type circuit. I'm going to bend your brain a little bit because I'm going to reference this address as an input and not just an output. Okay? Go into program mode. I'm going to set up what's called a seal-in circuit. This is very common on industrial machinery. This will be the start button, and over here will be the stop button. Okay, now I'm going to make the stop button a normally closed switch, and the start button a momentary, normally open switch. It's normally open because normally it doesn't pass power. This is normally closed because in its unpressed state it passes power. Okay? Now, like I said, I'm going to reference the output address as an input. Now let's think about what's going to happen here. When I press the start button, I can't reach it. Let's see. I have it pointing there. Well, I can't reach it, but it's up there, right? When I press the start button, that set of contacts or that instruction is going to pass power. since the stop button is normally passing power, that's gonna pass power also, and the doorbell's gonna come on. Maybe I should make this the motor instead of the doorbell, because it's really irritating. Because what'll happen is after I release the start button, since the stop button is still pressed, the doorbell will whir around the start button, right? The output will whir around and cause the output to remain on. Okay, so let's try this. All right, let's download, and so that we don't go crazy thinking that this is going to be a doorbell, let's call this motor. Okay. Download it, run, and we press the start button, motor turns on, release the start button, motor continues to run. The only way to shut it off is by pressing the stop button. Okay. This is very common. If you notice when you pass the switch around, if everybody got to see it, this is a momentary push button. Okay. When you press it, it may make contact or break, whichever is the case, but when you release it, it goes back to its default state. And these are very common. Instead of using light switches for on-off for machines, we use stuff like this. Okay. These are much more reliable than the other type of switch as well. Okay. So this is a circuit that is called the seal-in circuit. It's basically the memory circuit where it remembers that something happened, the button was pressed, and it changed the state of the machine. Okay. Well, I see that I'm out of time, so I will see you guys again on Thursday. At that point, you will probably start programming. Do not forget to bring your CD. Please bring your CD.